Okay, and I'm back. So anyway, I just wanted to say that, I wanted to show you how you could get the same answer to example number 8 by using tabular. So now let's use tabular to solve example number 9. So this is our integral, and you can imagine that exponential on Lipit is at the end, so our exponential is going to be what we take the integral of, and our polynomial, it will be what we take the derivative of. So the derivative is nice and easy. So that'd be 3x squared, that'd be 6x, that'd be 6, that'd be 0, okay? When I'm taking the integral, this is going to be 1/2 e to the 2x. Then we have 1/4 e to the 2x. Then we have 1/8 e to the 2x. And then we have 1/16 e to the 2x. Because remember, when you're integrating, you are, dividing by the derivative of this 2x. So when I integrate e to the 2x, it's going to be e to the 2x divided by 2. Okay, so that's why, and then I had to do that again on the next one and again on the next one. So now, when we look, and I'm going to change my color again because I do think that it's easier to see. When I'm taking this times this, remember, it's times +1, and then this times -1, this times this times +1, and it just keeps going like that, times positive, negative, and this last one times -1. So when I do the multiplication here, I've got 1/2 times x to the third times e to the 2x times +1. And so I'm going to write that as x to the third divided by 2, e to the 2x, okay? And then I've got the 1/4 times 3x squared times -1, so that's -3x squared over 4 times e to the 2x. And then this one, I would reduce that 6/8. So the 6/8, and when I look, they're all positive. So that's going to be 3/4. So that's 3x over 4 e to the 2x. And then this one's going to be negative, and divide by 2. Oops, that 3 did not look like a 3. 3/8 e to the 2x. And then plus c. Okay, so that is much easier than having to use integration by parts multiple times. It doesn't always lend itself to using tabular, and I'll show you an example, this next example, well, not the next one. 11 is when you won't be able to use it, okay? But 10, it says use the tabular method to integrate. So this one should be pretty easy. We've got x squared, 2x, 2, and 0, because we just take the derivative all the way down. And then for the sine for x, when we integrate, what can I take the derivative of that will give me sine? Okay, that would be negative cosine, but we have to remember to divide by 4. So negative cosine of 4x divided by 4. What can we take the derivative of that will give us negative cosine? That would be negative sine. But we have to remember to divide by 4. It gets multiplied by this 4, so I'm actually dividing by 16. And then the next one, what can we take the derivative of that will give us negative sine? That would be positive cosine. So we've got cosine of 4x, but then we would be dividing by 4, and 16 times 4 is 64. Okay, so we've got that filled out. Now let's go ahead and connect. Remember our +1, -1, +1. So this +1 gets multiplied times the negative, and the x squared over 4. So we've got negative x squared over 4 cosine of 4x. And then for this one, it's a negative times a negative, so that's going to be a positive. And divide by 2 gives me x over 8 times sine of 4x. And then the last one is divide by 2, but it is positive. And that's going to be 1 over 32 cosine of 4x plus c. Okay. I just checked it with my answer that I did on my paper, because sometimes when I'm on this, I seem to do things weird sometimes. But that gets us through that one. And it says, no, a special note here, after each application of integration by parts, watch for the appearance of the original integral or some multiple of the original. So for this one, notice that e to the x never goes to 0. Cosine x never goes to 0. If you've got two functions that never get to 0, then tabular method really doesn't work. Okay, so we are going to have to use our integration by parts, and then it said watch for the appearance of the original integral. So we're going to try and watch for the appearance of this integral. And when we look at Lipit, I don't have a logarithm, I don't have an inverse trig, I don't have a polynomial, I have an exponential. Okay, so the exponential is what they're wanting us to make our u. So if our u is our exponential e to the x, our du is e to the x dx. Our dv then would be cosine x dx, and if we integrated both sides, our v would be sine x. Okay, so now we're ready for our u times v minus the integral of v du, and I'm going to put the e to the x first. And now we're going to, again, we've got e to the x as our u. So our du is going to be e to the x dx. Our dv then would be sine x dx. And if we integrate both sides, we get negative cosine x. So now e to the x sine x minus, now remember, put a bracket because this integral is going to be the u times v. So negative e to the x cosine x minus the integral of v du. So this would be negative e to the x cosine x dx. And let's just clean this up with all those negatives and everything. Minus a minus is a plus. And remember, this is a plus, but then this negative out here that's in front of this bracket gets multiplied by that. So this negative goes in front, and then this is integral e to the x cosine x dx. Now remember, they told us to watch for this, right? This is our original. Oops. Grabbed the wrong thing. Oops. Sorry, guys. This is our original. I don't know. There. Integral e to the x cosine x. Look, we've got integral e to the x cosine x. Okay, this is what they were talking about. They wanted us to keep an eye out for that. Because if we kept going here, like, even though we kind of made our little box for our integration by parts here, this is actually what it's equal to. So look, integral e to the x cosine x dx is equal to this. Well, now look, I could actually add this to both sides. So if I added this to this side too of the equal sign, I would have two of them on the left-hand side. So let's say I'm adding that. Look, that one goes away. I now have 2 integral e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x, okay? Because that one went away, but I brought it in over here. And then we can divide both sides by 2. Or if you want to think about it as dividing everything by 2. Now, when you're using this method, you have to remember to put your plus c on the end, because this is an indefinite integral. And so this is going to be e to the x over 2 times the sine of x plus e to the x over 2 times the cosine of x. Oops, sorry. It doesn't like it when I hit it right there. And then plus c. So this is your answer. And what did we do again? Well, we had to use it multiple times because we knew it wasn't going to stop. So it has to work out this way because it doesn't stop. So at some point, you're getting back to where you started. And so the technique is, okay, once you see that, then go ahead and add it to both sides so that you can combine them, okay? Now, number 12, it says challenge. And I think our challenge, we're going to first just try to make our u that square root of x and see what happens. Our du is going to be 1 over 2 times the square root of x dx. And if we multiply by that denominator on both sides to solve for our dx, you're like, ooh. So if I had integration of sine u and then I put my equivalency for dx in, it looks like I'm still going to have an x. But when I realize that square root of x is u, I'm going to bring the 2 out in front, I can say u sine u du, right? Because I basically just replaced this with a u. I brought the 2 out in front, and I put the u in front of the sign. Now, I could use tabular here. U, 1, 0, sine, negative cosine, negative sine. And then positive 1, negative 1. So this is going to be 2, and then I've got my negative u cosine u, and then a negative times a negative is positive sine u, and then plus c. So now we need to distribute our 2 and put our u back in. So our u was the square root of x. And we did it. So what did we do again? We chose that up as our u. We took our du to find our dx. We realized that we had extra left over, but thank goodness the extra that was left over here that had an x in it, I could make it some form of u. So don't give up if you don't get rid of all of your x's, because sometimes you can still save it, okay? So that is lesson 9.